Why do we call COVID-19 a coronavirus? When I think of a corona, I think of the sun. It's a part of the sun that sticks out from its center, its outermost layer. Likewise, all those spikes sticking out from the virus's center are the COVID-19's corona. And that corona is part of what makes COVID-19 so dangerous. Let's take a closer look. What are those spikes anyway? Each of those spikes is a protein called spike protein. One is made of two layers, and the COVID-19 uses it to break into the cell. If the cell was a house and a COVID-19 variant was an intruder, then the spike protein would be the COVID-19's handy house key. On the walls of a cell are receptor proteins that act like doorways, taking in signals from molecules outside the cell like hormones and nutrients. One of these receptors, called ACE2, are what a COVID-19 spike protein targets. A spike protein can bind itself to the ACE2 receptor like a key fitting into a lock. The unique shape of the protein's S1 layer that lets it bind to the ACE2 receptor is like the unique cut of a key that lets it fit the lock. But after binding to the ACE2 receptor, the spike protein sheds its S1 layer and its S2 layer takes over. Like a key rotating the lock to get the door open, the S2 layer changes its shape and orientation to let the viral membrane fuse with the cell membrane and create an opening into the cell, where the intruder can make more copies of itself. Although that handy house key is the COVID-19's asset, it's also its downfall, because that spike protein key fits more than one lock. After recognizing that the COVID-19 is an intruder, the body begins to send out white blood cells, essentially security guards, to dispose of the intruders. A single B lymphocyte has many receptors sticking out from its surface that can bind to a single protein antigen, like a COVID-19 spike protein, just like a lock match to a key. After a B cell successfully binds to the protein, with assistance from a T cell, it transforms into a plasma cell that can release tons of antibodies which can bind to COVID-19 surface proteins, again just like locks to keys, and neutralize the COVID-19's ability to break into the cell. The B cell also leaves behind versions of itself called memory B cells. So if the COVID-19 ever comes back, the B cells can respond again, but faster. Knowing both the shape of the COVID-19 and that our bodies can learn from experience, we can take action. We could create a vaccine that uses COVID-19 surface proteins. What if we were to design a harmless nanoparticle that's packed with the COVID-19 surface proteins that are most useful to attack, arranged in patterns that make it easier for the body to recognize and remember them? We could give the body the experience to prepare for the intruder before it arrives.